All right, so welcome back. Hope everybody had a great vacation and 1 quarter left. This quarter ends, third quarter ends on Friday, and it's just 1 quarter left and we're done. So as you know, we were supposed to have a test on the Thursday before break from school. So the test was actually postponed until this Friday. So let me just talk about what we're doing this week. There's a couple topics that there was no Delta Math for, and there was no IXL for. So I decided to kind of skip those topics. And now that we have a little bit of time, we're going to actually do those topics that we were going to skip. Okay. So the homework for this week is actually on Google Classroom because there's no Delta Math and there's no IXL for those topics. Those assignments, there's 3 assignments there. Those assignments were posted this morning, and I've gotten some messages that says that 2 of them didn't have attachments to them, so I have to fix those assignments. But for the one for tonight, it should be all set and it's up there. All right, so the plan for the week is Monday, Tuesday, Thursday, we're going to talk about just additional topics. Wednesday, it'll be just a free day, no quiz or anything like that. And then Friday will be the test. Okay? Any questions on that? And the test is actually going to count towards the 4th quarter because quarter ends Friday, but the test corrections aren't due till Monday. So the test will count towards the 4th quarter. Okay? All right. So today we're going to talk about areas of regular polygons. And by the way, there is no Regents exam in geometry this year, but I don't want you to feel like we're missing stuff because honestly, we've been following pretty closely the Regents curriculum. So it's probably not as rigorous as it normally would be because everything's open note and all that stuff. And so, you know, it's sort of up to you how well you learned it. But in terms of actual content covered, I feel like you guys should be fine at the next level as long as you were reasonably conscientious about actually learning stuff this year, which, you know, some people should have a little bit, but, you know, I was able to control what I was able to control this year, and other things sort of it's up to you. So I know that some students are a little worried about their ability to like do the math at the next level. I think you guys should be fine. So there you go. All right, so areas of regular polygons. So first, I want to use some definitions. Earlier in the year, we defined what a regular polygon is. I'm just going to reiterate that definition. So remember, a regular polygon does anybody remember what that is? Does regular mean geometry?
All sides are congruent?
Yeah, all the sides are congruent and all the angles are congruent. It's equilateral and also equiangular. Okay, so remember, a regular polygon is both equilateral which means all sides congruent, and equiangular. Which means all angles congruent. Okay, so like, for example, a square is an equilateral quadrilateral, or it's a regular quadrilateral, sorry, a square is a regular quadrilateral. Or a stop sign is a regular octagon, right? A little harder to draw, but best here. Okay. A regular polygon is just all the sides are congruent and all the angles are congruent. There's two other important definitions that we should talk about. First is the radius of a regular polygon. So we know what the radius of a circle is, right? The radius of a circle is just the distance from the center of the circle to the circle itself. So what do you think the radius of a regular polygon is? Somebody guess. You're probably right.
One side.
Close.
Half of one side.
No, it's the distance from the center to the corner, like any corner, any vertex. That's the radius. Does that make sense? Like in terms of what you know about the definition of the radius of a circle, that's pretty consistent with the radius that I just gave you. It's the distance from the center of the polygon to any vertex. Okay? Radius of a regular polygon is the distance from the center of the polygon to any vertex. Okay, so the radius of a square would be the distance from the center of the square to the corner of the square, like that. That's the radius. And it could be the distance to any corner, be the same, right? So if I have an equilateral triangle, which is really a regular triangle, right? An equilateral triangle is a regular triangle. The radius would be like the distance from the center to any corner, like that. That one would be fine. Or a pentagon. Say I have a pentagon. Well, that's not very good. Okay. It would be the distance from the center to any corner, like that one. Okay? And one more important vocabulary word is the apothem. Of a regular polygon. And this is probably a new word. Has anybody heard that word before? Apothem? Okay, so the apothem of a regular polygon is the distance from the center of the polygon to any side drawn perpendicularly. Okay. So again, if I have a square the apothem of a square would be the distance from the center of the square to the side, drawn perpendicularly. That's the apothem. It's definitely different than the radius. Right? And I can do this for any size polygon. I have a little polygon drawer here. Let's say I have a octagon. This way easier for me to draw than it is for you to draw out. And so the apothem of an octagon would be the distance from center to any side. It doesn't matter. Any side, like this side would be fine. Drawn perpendicularly, that would be. Yeah. Okay, so we have a regular polygon, which is just equilateral and equiangular. We have the radius, which is the distance from the center to the corner. And we have the apothem, which is the distance from the center to the side, perpendicularly drawn. Like the altitude, right? Oh, no, it's not that. Never mind. All right, so yeah. So an important thing is, like, if you compare, like, for the same polygon, the radius and the apothem, which one is longer? Radius, definitely, right? Because if you think about it, like, I could have drawn like this little right triangle here. This is the apothem, that's the radius. The hypotenuse of a right triangle is always the longest side of a right triangle, so the radius is always greater than the apothem. So that's an important thing to keep in mind here. Fact for any regular polygon. Radius is greater than the apothem. Okay. Another important fact about special segments is that all of the radii is plural for radius, all of the radii of a regular polygon, that all radii of a regular polygon when drawn together split the polygon into n congruent isosceles triangles. Where n is the number of sides of the polygon. So kind of a lot of words there, but basically what it's saying is if you draw in all the radii of a polygon, it just splits it up into congruent triangles. That's the main idea. So if I have a square again, and I draw in all four radii, I know a square is equilateral, so those sides are all the same, right? If I draw in all four radii, so the line segments going from the center to each corner, like that, I know they're all the same length. So these four triangles, they're isosceles and they're congruent, and there's four of them. That's all this is saying. The same thing would be true if it's a pentagon or something. Like if I have a regular pentagon, this, and I draw all five radii in this case, yeah, like the Chrysler symbol, right? you end up with 5 congruent isosceles triangles. Does that seem logical? If it's an octagon, you're going to end up with 8 congruent isosceles triangles, right? If it's a decagon, you'll end up with 10 congruent isosceles triangles. So if we're trying to calculate the area of a regular polygon, doesn't it make sense that we could just calculate the area of one of these triangles and multiply it by the number of triangles that there are? Like in this case, I can calculate the area of one of these triangles and multiply it by 4. In this case, I can calculate the area of one of these triangles and multiply it by 5. If it was an octagon, I could calculate the area of one of those triangles and multiply it by 8, right? That's the process that we're going to follow, and it works every time. So, to calculate the area of a regular polygon, just find the area of a triangle formed by 2 consecutive radii and multiply by the number of triangles there are. Okay? So, like, for example, let's suppose we have a regular hexagon. Right, so I'm going to try to draw regular hexagon. And let's say that the side length of this regular hexagon is 10 inches. If I draw in one of these triangles formed by 2 consecutive radii, this, then definitely the area of the hexagon is equal to the area of one of those triangles times 6, because in this case there would be 6 triangles that you could draw that are all the same size. Okay, so far? So the area of one of these triangles is just 1/2 base times height. Well, we don't quite have everything we need. We know the base of this triangle is 10, but we don't quite know its height, right? The height is actually the apothem of the hexagon itself, right? This is going to be, the height of the triangle would be A, apothem, the hexagon. So we need to figure out what that is. Now, the reason why I chose a hexagon is because hexagons have a really convenient property that this triangle is actually equilateral. And how do I know that? How do I know that this red triangle is equilateral in a hexagon? It's not true for other types of polygons, like this is not an equilateral triangle. This is not an equilateral triangle. If it was an octagon, it wouldn't be an equilateral triangle. But why is it an equilateral triangle for a hexagon? How do I know that? Yeah.
It's totally a guess, but is it because the number of sides is like a multiple of 3 or something? And a triangle has 3 sides?
Might have something to do with that, but that's not directly why. The direct reason why is because How many degrees are there in a complete circle? 360. So how many degrees are there in this angle up here? 60, right? Think about it. It's going to be 360 divided by 6. This is going to be 60 degrees. But I know this triangle is at least isosceles. Base angles are equal. If this is 60, that means these two have to add up to 120, and they each have to be 60 because the base angles of an isosceles triangle are congruent. So this ends up being a 60, 60, 60 triangle that's equilateral. Does that make sense? It wouldn't be true for other types of polygons. Like if this was a pentagon, for example, this top angle here would be 72. I'd take 360 divided by 5 instead of divided by 6. You get 72, which means these two have to add up to 108. This would have to be 54 and 54. This is definitely not an equilateral triangle, right? Same thing here. This angle would have to be 90, 360 divided by 4, which means these two would have to be 45 and 45. If it was an octagon, that top angle would have to be 45, because you take 360 divided by 8. The bottom angles would be decimals. It would be like 135 divided by 2 for each angle. Does that make sense? So you can find these three angles for any polygon, but for a hexagon in particular, it's nice and convenient because it ends up being equilateral. So that's a good one to start with. All right, so now if I'm trying to find the apothem, then, right, A, I could use the fact that this triangle right here is 30, 60, 90. And I know that this is 5, 5. So if I know the short leg of a 30, 60, 90 triangle, how do I find the length of the long leg? Remember we did that earlier this year? Close. Radical 3, right? Radical 2, you multiply if it's a 45, 45, 90, an isosceles right triangle. But if it's a 30, 60, 90, you multiply by radical 3. So A in this case is 5 radical 3. Does that make sense? So back to the question at hand, which is to find the area of the whole hexagon. It's just going to be the area of one of these triangles, which is 1/2 base times height, 5 radical 3. That whole thing times 6. And we can simplify this a little bit, like half of 10 is 5. 5 times 5 radical 3 is 25 radical 3 times 6. And I can multiply the two numbers that are both outside the radical, but I can't multiply something that's outside a radical by something that's inside a radical. So this ends up being 25 times 6, which is 150 radical 3. What would the units be here? Yeah, this question?
Yeah, just really quickly say again how you look at it.
Yeah, in general, for any 30, 60, 90 triangle, if this is 30, 60, and 90, if you know the length of the short side, which is right here, remember the ratio of the sides is 1 to radical 3. So if you know the length of this side, you multiply it by radical 3 to get this side, right? So if this was like 5, this has to be 5 radical 3. If this was 8, this would be 8 radical 3. Okay? So what are the units here? Inches squared, because we're talking about area still, so the units are still going to be squared. That's the exact area of this regular hexagon. Now, if I take this formula, like in general, this formula right here, in general, the area is going to be 1/2 S times A all times N. S is going to be the side length of the polygon. Because that's the base of the triangle, is the side length of the polygon. A is the apothem of the polygon, because the apothem is the height of one of those triangles. And then n is the number of sides in the polygon, because that's going to be the number of triangles that there are. So this is the formula we're going to apply every time. Okay. Now, what if we do a problem that it's not a hexagon, so these aren't aren't equilateral triangles? Okay, it's still possible to do. We just need a little bit more information. Like, suppose you have a regular pentagon. Can't draw perfect pentagons. Just use your pentagon drawer. It's right here. Just click this button and press 5. You don't have it. Okay, so yeah, just do the best you can. So if I have a regular pentagon like this, let's suppose they gave us the radius and the side length. Let's say the radius was 6.1. This distance, 6.1, and let's just say it's centimeters. And let's say the base is 7.2 centimeters. So just like before, exact same process. If I draw one of these triangles in, then the area of the whole thing is just going to be the area of that triangle times 5 in this case, right? Because there's 5 triangles that you could draw. So what we're missing here is the height of the triangle, the apothem of the pentagon, right? That's what's missing. So if you take this triangle out of context, we have an isosceles triangle where this is 6.1, this is 6.1, and this is 7.2. And we're trying to find the height of the triangle right here. Okay. So the first thing I'll say is, for any isosceles triangle, when you draw the altitude in like that, it actually splits the triangle's base into 2 equal pieces, right? This is going to be 3.6 and 3.6. So there's a couple different ways I could get A. I could get A by doing the Pythagorean theorem. I could say A squared plus 3.6 squared equals 6.1 squared. That would work, right? Because there's a little right triangle right here. Here. Or I could use SOHCAHTOA. And I think that would be a little less work, so I'm going to do it that way. I'm going to use SOHCAHTOA. I know that this top angle, like I said before, is 72. How did I get that again? Yeah, I took 360 divided by 5. Okay, 360 divided by 5 is 72. So each of these angles then has to be 36 and 36. So I could use SOHCAHTOA. I could either use cosine, because the cosine of 36 would be adjacent over hypotenuse. Let me write that. The cosine of 36 degrees would be adjacent A over 6.1. Or I could have used tangent, right? I could have said the tangent of 36 is equal to opposite over adjacent, 3.6 over A. One or the other. It doesn't really matter which one you use. You can use whichever one you want. I can't use sine. Why can't I use sine, really? Yeah, the fraction wouldn't involve the side I'm trying to find. That would be pointless, right? So I could write the sine function, but it's not going to help me find A. Okay, so then cross multiply here. A is equal to 0.1 times the cosine of 36 degrees. So on my calculator, if I take 6.1 times the cosine of 36 degrees, I get 4.935, blah, 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 blah. So now I can go back to answering the question that I was trying to answer all along, which is the area of the whole pentagon. Now that I know what its height is, the height of one of those triangles, I can calculate this. It's going to be 1/2 of base, 7.2, times height, 4.935, all times 5. I don't have to round anything because I have it on my calculator unrounded, 4.935. I could just say 0.5 times 7.2 times the previous answer, unrounded, times 5. That's everything. So the answer would be 88.83 if they wanted it to the nearest 100. 88.83. And this would be centimeters squared. So your goal for every problem should be to know what the length of the side is of the polygon, because that's the base of the triangle. To know what the apothem of the polygon is, because that's the height of each triangle. And then to obviously know how many sides there are. Because once you know those 3 pieces of information, you can just plug them into this formula. 1/2 base times height times the number of sides. Does everybody understand that? So to find the missing information, whether it's the base, which is the length of the side, or whether it's the height, which is the apothem, to find the missing information, you might have to use Pythagorean theorem. You might have to use special triangles if it's a hexagon. You might have to use trigonometry, not a hexagon, but that's it. You can use one of those things. Any questions? And maybe they might just give you everything you need, just straight off the bat, and then you don't have to do any of that stuff. You just apply the formula. Okay? All right, so the homework's on Google Classroom. It's been posted already, like I said. If you don't know how to submit things by Google Classroom, which you should have done that lots of times in other classes by now, but if you and in here also for the test review for extra credit, if you haven't done it yet, then Google how to do that because it's super easy. Don't email me your homework, please. It just like totally is overwhelming. So submit it through Google Classroom. You just take a picture of your assignment and then you submit it right on Google Classroom. Any questions? Okay.